approved that one already.
Who's giving the numbers? Who knows what those games are?
Okay, so any questions about what we've been doing so far? You might be wondering why. So just, we'll hopefully get to the why in a little bit.
I got
But
a quick question about the lab.
Sure.
Are we going to be utilizing SimKit tomorrow? SimKit?
yes, so yeah, the next computer assignment or the first will be posted this afternoon, so you get a chance to kind of take a look at it. What you, in preparation for it though, you should create your GitLab repository for this class, exactly as you did for the last class. And I think you've done yours already, so you're all good.
I did it because I thought I think I already did it.
Yeah, you did.
I don't know if
You did.
I did it correctly, but I'm
Yeah, no, it,
Are there instructions for how you want us to do that somewhere? I just wasn't in the previous.
yeah,
class.
there's,
There's a video. I sent it to Jose. I'll send it to you, Nick,
Okay.
the video.
yeah, there's,
Well, second question. So I downloaded the SimKit file. It seemed like when I was looking at the instructions, there's another application we had to download.
no, just NetBeans.
Okay.
And you just need to extract it. There should be a link to a video about, that walks you through how to do that. If not,
Is that in another YouTube channel that you created?
yeah.
Okay. Is that link in the Sakai? I'm sorry, I'm asking.
Yeah, if you go to the, okay, let's see, where are we? Of course, I'm logged out. Yeah, if you go here, implementing discrete event models in SimKit, I kind of, this is sort of the list of all that you have, and then there's a link to this video, which should, let's see, if you've, okay, now for some reason it puts me on the guest, which is a totally useless one. All right, come on. So this, if this ever comes up, it kind of walks you through the process. In fact, even gets you started on the first assignment. So.
This might be a little bit of an out of scope question, but is SimKit actually used for anything in practice, or is it more kind of like a toy example framework for classes like this?
Well, let's see. Do you know Combat 21?
Only by reputation.
Okay, it uses SimKit. The Army's Log Battle Command uses SimKit. There are a number of other Army models that use it, and the Navy simulations that I'm developing for NavSup all use it.
So it's pretty constrained use from the DoD. I mean, like,
Yeah.
in terms of how it's being used so far.
Yeah, in terms of how, it's an open source model, so I've heard of people using it out beyond DoD, but it is a general purpose thing, and it seems to be pretty robust in terms of its ability, so based on its use in some of these DoD applications, at least, I would say it goes beyond a classroom toy.
I was looking for the Python version you mentioned. It seems like there's actually two out there. One which you're listed on as a developer, and one
Mhm.
which you're not listed on as a developer, but seems like a pretty just like straight rip from the Java stuff.
Yeah, I only know the one that I've done, and again, the Python one hasn't been tested as much as the Java one. I mean, it's been used for a number of theses so far, but so it hasn't really been stress tested as much as SimKit has. When just when they were developing Combat 21 at White Sands Missile Range, they it was sort of funny. Every time they would hit sort of a bug, they would immediately blame SimKit, and then they would look into it and realize, no, SimKit was fine. It was the other thing. So that, and so it's. I'm not entirely unbiased in that, obviously, since it's something that I developed. But like I said, it has been used. So. Okay, so one of the reasons why it was fairly straightforward to implement it in Python is that it's based upon this event graph methodology that we're going to start talking about. And an event graph methodology is based upon the discrete event methodology that we've talked about so far, which consists of creating models by defining parameters and state variables, and then specifying the state transitions for each of those state variables, which we identify with events, and then finally identifying which events schedule other events. And what I like about this methodology, which I didn't invent, is that it's very simple. And yet it's as simple as it is, it can be used to create very complex and evocative and expressive models. So we're going to start talking about that today. So, what is it? Give a couple of examples, reworking the two that we've done so far, and then another piece that I hope you kind of take away from this is something that you might have encountered before, is the idea of iteratively creating models. In other words, instead of trying to create a big model from the ground up, basically do it in steps. How do you eat an elephant one bite at a time? So the way that translates here is to begin with a fairly simple model that captures the essential elements of what you're trying to model, but then examine it for assumptions and make sure that you haven't missed any important ones. And we'll see a specific example of that as we go through this. So here's the essence of this event graph methodology. The idea is, are you familiar with the term graph in this context? I mean, you're probably familiar with the graph like a chart, but have you encountered a graph in the sense of nodes and arcs?
We had a discrete math class last quarter.
Okay, so yeah. So the idea of a graph is an extremely powerful and wonderfully simple way of creating models. And if you've had a discrete math class, you've seen a lot of really nice, elegant ways of capturing situations using graphs. And that's why this is such, in my view, such a compelling one. So a graph consists of nodes and arcs. A graph can be directed or undirected. And so with event graphs, they are directed. Our nodes are going to be identified with the state transition. And remember, a state transition is something where at least one or more state variables changes from one value to another value. We've seen some examples of that. That happens in 0 simulated time. So with each event kind of occurs simultaneously. And so what the edge is that scheduling relationship. So the canonical representation is, okay, here we have event A and event B, and the directed edge or arc from A to B says when A occurs from the event list, it schedules event B. Now, this is just the canonical representation of this relationship. When we start to see event graphs, we're going to have a bunch of nodes and a bunch of arcs. Now, there are two additional elements that are kind of added to this. Okay, the first is this Boolean condition, which is an option. It may or may not be there. And so the idea is that when event A occurs, if this condition is true at that point, then it will schedule B, and if it's not true, then nothing happens. We've seen an example of that, which we'll kind of go back to. Why is my pen black? I don't know why. But the second element on the edge is a time delay. So the T here says that when event A occurs, event B will schedule T time units in the future. And just to avoid clutter, if the condition is always true, then we can leave it off. So in contrast to almost all programming languages, the default for the Boolean condition is true, not false. So you have to be a little careful with that when you're programming, because the default Boolean, as you know, is usually false. The second is the default value of T is 0. That is a 0 delay, and we've seen an example of that in our multiple server queue example, which we're going to circle back to. So if the delay is 0, then we usually leave it off, just to avoid clutter on these things. Okay, and that's almost everything. Almost. So as we start to go into this, we're going to add some things like arguments on the events and priorities and some other things. But this is enough to just get started. So here are the steps to creating an event graph model from a problem description, which is something which, starting next week, I'm going to be asking you to do for some written assignments. So the first is to define the parameters. And the reason why that's a good place to start is because that comes from the problem description. In this class, that will be given to you. And so you can usually just kind of read what the problem is and write down the parameters. They come immediately from that. When you're creating a model out in the wild, that usually takes a little bit more time / negotiation with the sponsor, whoever's creating the model. But again, even in that case, it's usually fairly straightforward. So for example, in the models I'm developing for the Navy, they have very extensive databases which have information about all the different NINs which they have, and that those databases provide about 80% of the parameters that are used in the model. So we just sort of take them out basically as they are. The more challenging piece in defining the variables are the states. And that's where just getting some experience helps a little bit. Because defining the states are really kind of an abstraction of things. As we've seen in our multiple server queue example, I think most of you can kind of conceptualize what that is. You know, just think of your experience, whether it's getting coffee at Starbucks, or getting an in and out, or going to the DMV, or going to the bank, or we encounter these queuing situations again and again. In the multiple server queue model that we've developed so far, all we're doing is just counting things. The state is how many customers are in the queue, how many servers are available. that obviously leaves a whole lot of information about the system out. But for the kinds of questions that we're asking of this system, at least initially, that's sufficient. If we're asking things like, what is the average number in the queue, or what is the average utilization of the servers? Those are two of the main questions that we would be interested in for a system like that. And those can be answered with those simple state variables. Now, if there are deeper questions that, or more questions that we want to ask of the situation, then our model needs to be expanded to typically incorporate other state variables. Remember that state variables need to include initial values. That needs to be done explicitly. Because as we've seen in the multiple server queue, the initial number of available servers was equal to the total number of servers that we had in our system. So that needs to be specified. Otherwise, because the state variables change with the events that we define, they need to start somewhere. So that's the next step, is to identify what those state transitions are. In other words, and the way we do that is that if we have done an expressive enough job in defining our state variables, then we can just one by one pick a state variable and ask what can cause this state variable to change. And every possibility becomes an event. So with the number in the queue, what would cause it to go up by 1 is a customer arrives and joins the queue. What causes it to go down by 1? The customer goes from the queue into service. Those are the only, in that particular case, those are the only things that change that particular state. In a more complex model, you might have more than 2 events that change a state. Or you might just have 1 event that changes a state, as we have in the arrival process, which just has, we're counting the number of arrivals, we just have the arrival, just 1 event. So once we've identified all those state transitions and we write them as events, then we identify the scheduling relationship and we write those as directed edges. Okay, so what, okay, so let's see how this is applied to a model that we've already developed in a very verbose way, which is our arrival process. So we define our parameters. So for all the arrival process is doing is just counting the arrivals. We define our parameter, in this case, just 1 parameter, and keep in mind that a parameter can be a sequence of times like this, which are typically generated with a random variable, as you will see tomorrow. We define our state variable. In this case, our state variable is just the number of arrivals, and its initial value is 0. And then our state transitions are just, for the run event, we have the initial value of n as 0, and then when we have an arrival, we just increase it by 1. Okay, so this is how we've defined our parameters, our state variables, and our state transitions. And so the next step is to define our events. And what I'm going to do, I want to do this on the board for you. So what we do is we take, okay, remember our states are n with an initial value of 0. So we can always begin by writing down the run event, because if we have defined our state variables completely, including the initial value, then we simply write all of those in the run event. Now the state transition was that the number of arrivals increases by 1 when there's some event, and it's up to us to define what that event is. I call that event an arrival, but you can call it anything. Just don't call it late for dinner. So this is the next step. And then notice that having identified the state variables and the state transitions, I just write the events without worrying about the scheduling yet. In other words, if you just kind of do this step by step, then you at least have something written down, and then now it's what causes these events to schedule each other. So the run event will schedule the first arrival with a delay of the inter-arrival time. Remember that was our parameter. And just by way of notation, see, a curly brace denotes like a set or a sequence, right? And without it, we're just picking off the next one. That's what we're doing. In practice, when we implement this will simply generate the next random variable that we have. And I notice that because there's no condition on this, we leave that off. So if there's no condition, it means it always happens, it's always true. And then each arrival schedules the next arrival with a delay of T sub A, that is the inter-arrival time. So this is the model. This is the model right here. And again, notice that there's not a single line of code, and which is good news for some of you. Although the bad news is that at some point you got to put it on the computer. The good news, though, is this. Unlike programming, once you have this event graph, and as you'll see this tomorrow, hopefully, implementing this on the computer, especially if you have a library which implements random variables and the event list and provides a base class that allows these kinds of things, it's just simply a matter of translating this onto the computer. In other words, you have the design of your model right here. And so it's just a matter of taking each piece of this and mapping it into the corresponding piece in the SimKit framework. Okay, so basically, this is what I just did. So again, the run event, we always have a run event. It's the equivalent to the main, and this is just basically what I had on the board. So the run event, the arrival event, and so we just have them as circles, and then we identify the scheduling relationships. We write those as edges. So run schedules the first arrival with a delay of an inter-arrival time, and then the arrival schedules another arrival with another delay. And so when one event schedules another event, then we draw an arrow between them. And as you can see, unlike many graph frameworks, you're allowed to schedule yourself. Not all graph methodologies allow you to do that. This one does. You know why? Because in this particular case, this event schedules itself, so we allow that. And so this is our final model. So the model consists of all the parameter definitions, all the state variable definitions, and the event graph. So when I ask you to do one, this is what I expect. So if I give you a problem that says, okay, here's the situation, create an event graph model. What I want is I want to see parameters, I want to see state variables, and then the event graph, like this. Okay, let's apply this to a slightly more complex example, the multiple server queue. So here we have 3 parameters. We have our inter-arrival times, which we're now identifying with customers. We have our service times, which is another sequence of values, which are how long each customer takes in service once they get to service, and then the total number of servers. The main advantage of this parameter, by the way, if we don't have that, then we would have to create a different model for 1 server, and for 2 servers, and for 3 servers, and for 4 servers, etc. Here, with a parameter that's the number of servers, we just have one model that's good for however many servers that we want. And the only case where this model would not meet our needs, which we're going to see in a little bit, is a situation where the assumptions that we have made in this model do not entirely fit the situation that we're modeling. We'll get to that in a second. Well, a little more in a second. But we're going to do this first. Okay, so our state variables, if you remember, were Q, the number of customers in the queue, which was initially 0, the number of available servers, which was initially K, because this is an implicit assumption here, that we are assuming that when we start the system that all the servers are idle, there are no customers there. And then the third state variable was the number in the system, which is going to be initially 0, and I forget if, again, this is in a way kind of optional to define separately, because we can always define it as a function of, if you remember, it was Q plus K minus S. So if you tell me Q and S, I can tell you L. So we don't necessarily have to define it explicitly, but I think I'm going to do it here. Okay, and again, I want to do this on the board for you, just so you can see that it's... I mean, it's easy to just kind of look at the final version and say, oh yeah. But it's something else to just kind of see it unfold. Okay, so we have, here are our states, and if you remember, our parameters are our inter-arrival times, our service times, and K, the number of servers. Okay, we can always start with a run event. And our run event just simply sets all of our state variables to their initial values. And again, if you've done, like when you're doing this, looking at a problem and trying to figure out how to do it, what I strongly encourage is not to just kind of boilerplate something, but just really go back to first principles like this, and define your parameters, define your state variables, start with the run event. Okay, so you now have a non-blank sheet of paper, which is, don't underestimate the power of that. A blank sheet of paper is just a major stumbling stone in making progress. So the fact that you can at least write something down is something. On a more practical level, if this is all you have, then at least you get some partial credit. So
All about that part too.
yeah. Okay, so what's the strategy is, again, once we've defined these, is let's pick a state variable, let's say Q, and say what causes it to change and how does it change. Those are our state transitions. And what causes it, one of the things that causes it to change is that a customer arrives, and that causes the queue to go up by 1. And we're going to call that arrival as well, with the understanding that this arrival is is not the same as the arrival in the arrival process, because this is a very different state variable. The n in the arrival process that was just counting the number of arrivals always went up. But as we'll see, this is going to go down. What could cause it to go down? The name is arbitrary. But just as with writing variables and methods in programming, you want your names to be reasonably descriptive, the names of these things. And so when we go from the queue to service, then the queue goes down by 1. And as far as at least for now, those are the only things I can think of that would cause this variable queue change. Now, keeping in mind that in a more complex model, there might be things that I'm missing. So it's almost never a linear process. That's why you need a big eraser. All right, let's look at the state variable S. The state variable S, the number of available servers. Okay, now the arrival of customer as an event is not going to do it, but when we start service, we're going to decrease this by 1. Okay, so we're going to start service only if there's an available server, but if there is one, we're going to lose it. And what else can cause it to change? Well, it could go up when we finish service, and I call that end service. Because when, what's happening in the system is the customer's finished with the server, and now there's one more available. Okay, those are the only times that I can think of for this state variable. And just in this particular case, okay, I've added this state variable, which is kind of redundant, but there's no rule that says we have to have the minimalist one. So let's look at this. What would cause the number of customers in the system to increase by 1? Well, we already have an event that does that, and that is the arrival event. And so that would increase, now we have one more in our system, which is the queue plus the ones in service. And what else could cause it to change? Well, when a customer leaves. So do we have, we have an event that represents that, and that's the end service event. Okay, so so now we're not, there's no guarantee that we're done, but we're done as far as I can tell. In other words, you do the best you can. And so basically this is now our model. Or these are, take that back, this isn't our model yet. These are our state transitions. These are our events. We've identified our events. And we might have to circle back and identify more state variables. We might have to identify more events if we've forgotten some. That happens. Okay, but as far as I can tell, we've identified all of the state transitions, at least for the state variables that we have. And now we move on to identifying the scheduling relationships. So the run event, just as with the arrival process, the run event will schedule the first arrival with a delay of an inter-arrival time. The arrival event will schedule the next arrival, just as with the arrival process. In fact, you can kind of see that there's kind of an embedded arrival process here, but we're not going to worry about that now. Now here's one of the trickier ones. Let's actually move to this one, just for when we start service. The time between when we start service and we end service is given by one of these service time guys. So that's kind of an easy one. Bless you. Okay, so now the arrival to the start service is something that we need to kind of look at. So an arrival will schedule a start service, but only under certain circumstances. And if you remember, there's a Boolean condition on the edge, and the condition here is that in English it would be that there is an available server, and we can express that in the language of our model by the expression s bigger than 0. In other words, the concept there is an available server can be expressed in the model as s bigger than 0. And that's important because, I mean, ultimately, if this stands a chance of being implemented on the computer, we need to be able to describe it using the variables in our model and not just with words. In other words, the computer doesn't understand words. Maybe Alexa does, but you know, that's even that is somewhat suspicious. But okay, and then finally, okay, now are we done? Well, we're kind of done with the arrival event because I can't think of anything else that the arrival event would cause to schedule. Okay, with the start service event, we scheduled the end service event with a delay of a service time. Is there anything else that it might schedule? And the answer is no, but you know, some things to think about. Does the start of a service schedule an arrival? No, because you know, just the arrivals are just kind of coming in from the outside, and whether they start service or not, that doesn't affect you know whether someone is coming in there. Now, in some models, it might, but we'll see examples where things like that might happen, but in this case, it doesn't. But then, okay, so we're through with start service. Now let's look at end service. So end service isn't scheduling anything. There's no law that says an event has to schedule something. So we might be okay, except that in our system, what happens when a server, you know, we go back to our system, what happens when a server completes service on a customer? What do they do? Yeah, well, we actually know, yeah, we see we have an available server because we just incremented by 1. The question is, what is it we are looking for? You're the server.
We're trying to queue the next customer.
Yeah.
To start the next service.
Yeah, in other words, if there's another customer, we want to serve, because if you're that customer, I mean, now, in reality, have you ever been kind of at the waited and waited and waited? You're at the front of the line, somebody finishes service, and the server goes on break. That's one of the laws of waiting lines. But in this model, the servers aren't allowed to take breaks. So we just kind of, so our server can't take a break. If there's a customer waiting, the server has to take them. And so how can we express there's a server, there's a customer waiting in the model? Q greater than 0, exactly. So that says that if there's somebody in the queue, then we will schedule, we'll start serving. If there's nobody in the queue, then we don't want to do that, because now one of the things that you should kind of notice here is that these Boolean conditions are actually kind of guarding this state transition, because particularly for state variables that must always be positive or non-negative. Like the number in the queue can never go negative. In the model it could, but in reality it can't. The number of available servers can never go negative in reality, but in the model it can if we're not careful. So when we see a state transition like this, that's potentially dangerous, in the sense that could, if that event occurs, and Q is 0 or S is 0, or both, then all of a sudden we have -1. Yes.
So we have the inner arrival times and service times as parameters, but they're not explicitly defined. How do we specify that in this construct? Like what those arrival times are? Would that be just in terms of a function or just an explicit list or?
Well, for this, great question. For the sake of the model, we leave that unspecified until we actually implement the model. I mean, as you saw in the example yesterday, we gave numbers to those. So yes, once the model is running, we have to actually put numbers in there. How do we put numbers in there? The main way in the program is with a random variable generator. So if you mentioned that you've seen the Poisson process before. If you want a Poisson process, then we make our inter-arrival times exponential. But notice that there are two things that guard this state transition. Okay, notice from the arrival, Q is always incremented, so Q is always going to be positive when it schedules this, and then the condition is that S is bigger than 0, so S is going to be positive. So when start service is scheduled from arrival, then this state transition can always be safely done. And likewise, from end service, S, the number of available servers, is always going to be at least 1. And because the condition is that Q has to be bigger than 0, that is at least 1, then the state transition can be safely executed. And I can tell you from experience that, especially in more complex models, sometimes that doesn't happen. In other words, sometimes a state variable can get into inadmissible values, and that is usually because there's an error in the model. So when we say that all models are wrong, we don't necessarily mean that there's an error. There are two types of wrong. One is the wrongness of omitting characteristics of the system you're modeling, and the second type of wrong is just being wrong. We don't want the second type. Okay, so basically in the slides I've just kind of done all that, and so this is pretty much our final event graph. And our complete model, it consists of the parameters, the state variables, and the event graph. Now, there are some implicit assumptions even in a situation like this. And it behooves us to examine these assumptions and see how consistent they are with the system we're modeling. So one of them is something called an infinite calling population. And what that means is that the arrival rate remains constant no matter how many are in the system. There are many situations where that's a reasonable assumption, even though it's never literally true, because there's not an infinite amount of anything. There are other situations where it is not a good assumption, and that's when we only have a handful of potential customers. So if our customers are carriers, then an infinite population is not a very good assumption. If our calling population are just sort of people on the peninsula, which are about 100,000 or so, and our system is Safeway, then if there are 50 people in Safeway, then that really doesn't affect the other arrivals as much. But that's something to look at. The other assumption is infinite waiting room. Now that's, in other words, as customers come up, the value of Q has no bounds on it. In some situations, that's a reasonable assumption. If you look at the food hut out here, there's practically no restriction on the amount of waiting room there. If you look at the drive-through in and out, for example, and people aren't very good about this, but if they were good about not blocking Del Monte, then when the cars go all the way out to the road, then all of a sudden, you know, if you're being a good citizen, you should go somewhere else. Okay, so that's a finite waiting room, and so for that system, this model would not be a good model because it doesn't capture the finiteness of this. Whereas for the food hut, it's a better model because they're really, you know, there's no practical restriction on that.
Even though there's not like a hard bound on it though, like you can easily imagine someone like going up, seeing a line that's really long, and be like, yeah, I'm not gonna wait long.
Oh yeah, absolutely.
How do we account for that?
Well, that's the next bullet point. One of the assumptions is that all arriving customers join the system. But you're exactly right. We look at our system and we see customers kind of coming up. They look at the line and they go, yeah, screw this, I'm going somewhere else. Our multiple server queue model doesn't do that. And here's another one. Once you join the queue, it's, you know, Hotel California. You know, you can never leave, right? That's how our model works. But then we observe our system, and so, you know, we're looking at the food hut there, and those lines get pretty long. And so it's like you've got a class coming up or something, and I thought I was going to make it, but, you know, and then leave the queue. The multiple server queue model that we've done doesn't do that. That's actually something called reneging. So these are the kinds of questions that you always want to be asking the model. You want to observe the system and match them with our assumptions. So for example, let's look at in our system let's suppose there's only a finite amount of waiting room. And the behavior that we observe is that when the waiting room is full, the customers leave before entering. In other words, they look at it, the system is full, there's no room to wait, and so they leave. In other words, now in practice, the in and out customers are not so good. They actually block Del Monte at times, if you've seen, but they shouldn't, but they do, and that's sort of another. But in a way, that's still another finite type of thing. Yes.
So we can make these assumptions that there's an infinite waiting room, but can you make your model and just state that we're not going to use this, or this is what we're going to use? In fact, that there's 20 spots in the queue maximum or something.
That's exactly what we're going to do. You know, in other words, the model isn't the be all and end all. The idea of sort of this iterative model is we look at it, we say, well, one key element that we're not capturing is that we have a finite amount of room. So let's add that to the model. That would be a parameter. That's a value that doesn't change. If we only have a capacity of C customers, and once that we reach C, we can't take anybody else, that's a new parameter. Now, what would we be interested in for a model like this? We would be interested in how many customers are we losing because of this finite capacity. Would it be worth it for us to expand our waiting room area or not? How many are we losing? That's the question. How could we answer that? Well, again, it's not rocket science. If we knew how many potential customers we had and how many customers we lost, then just the ratio of those two would be how many we're losing because of this finite amount. So we go back to our model, and we're not starting entirely from scratch. We have our previous model, our multiple server queue model, but now we have two additional state variables, the number of potential customers and the number of customers we lost. I'm calling that B for bulk. And now, in addition, our arrival event is going to increment the number of potential arrivals as we had before. And now I'm going to define a new event. I'm going to call it join queue, which is going to be like the previous arrival one, except that's going to be where we increment queue, because now we can't increment queue just because you show up. You show up, you may join or you may leave, and all the others are the same. And so this looks like this. So again, our run event, we can initialize all of our state variables. And now our arrival event, just like our arrival process, is just going to increment the number of potential customers. But now we have our join queue event, which may or may not be scheduled. And we have another event that are the number of bulks, and that's just going to increment the number of bulks. And everything else is pretty much the same. So the way we would kind of do this in terms of our scheduling edges is, just as before, we have our arrivals, which schedule the next arrival. And again, just picking off the ones that we already kind of know, once we join the queue, we have pretty much the same scheduling relationships as we had before. So we can, and again, it's just like, when you're taking a test, you always answer the easy questions first. I hope you all do that. So we answer the ones that we already know. Okay, so that's there. But now, the arrival piece, why is my pen not pen color? I thought it should be red. I'll make it red now. Okay, so arrival event we would either join the queue or not join the queue. So under what circumstance can we join the queue? Remember, we had a capacity of C.
Q is less than C.
So if Q is less than C, we can join the queue. But if Q is equal to C, then we bulk. And we have one more of those. So what we've done is we've examined the assumption that, and said there's a finite waiting room, and what happens to customers? They leave, they go somewhere else, and we just lose them. So we expand our state variables to include the number of potential arrivals and the number that we lost through bulking. And so we need to just basically we just kind of split our model apart a little bit and then just added the conditions. So again, none of these are laws of nature. These are things that the modeler imposes on your system. Okay, so now this afternoon, again, the